Newton's second law. When we discussed Newton's first law, we said that objects with no force on them continue at constant velocity. So now let's ask, what happens when an object does have a net force on it? Well, experiment shows that an object with a net force accelerates, and that acceleration is proportional to the amount of force and inversely proportional to the mass. So we can sum those observations up in a mathematical equation that is known as Newton's second law. The acceleration of an object equals the sum of all the forces acting on it divided by its mass. A little bit about notation. That's a Greek letter sigma. You might have seen that in math class before. It means to add things up. So this notation is saying there may be several forces. Add all the forces involved in the problem. And yes, these are vectors, so you have to do a vector sum, which you know how to do. Sometimes Newton's second law is written like this. Sum of the forces on an object equals object's mass times its acceleration. You probably see it this way more frequently. Because this is a vector equation, you tend to solve these problems by writing everything in component form. So this really means that there's three equations in here. An equation for x, and an equation for y, and an equation for z, if we're doing 3D. We won't do very many 3D problems in this class. Usually it'll be 1 or 2D. And also, instead of using x, y, and z, sometimes it's easier to solve problems using polar coordinates. So sometimes this might be like r and theta instead. But when we get to those types of problems, we'll use that different coordinate system. So this is a vector equation, and it's easier to do it in components. Now, the units of force. You can kind of see from this equation that the units of force are units of mass times units of acceleration, which in our standard system of units would be kilograms times meters divided by seconds squared. And to honor Isaac Newton, this combination of units is given the name newtons. With capital N for that combination of units. So you can write it either this way or just as N. Now, Newton's second law is going to be one of the most useful equations we use all semester. A lot of what we do in mechanics is combine Newton's second law with kinematics, and then we're able to describe motion. There are a few other equations that will be equally useful, like the law of conservation of energy, the law of conservation of momentum. But this is one of our major tools in our physics toolkit that will help us analyze problems. And over the next 2 weeks, we're going to learn how to use this for all sorts of situations. And really, I think this is the core of Physics 6. Our unit on Newton's laws is really the meat and potatoes of Physics 6. And what we generally do when we use Newton's second law is we kind of use it in conjunction with kinematics. So we often use Newton's second law to find the acceleration for a certain scenario. And then use kinematics to describe the motion, find the position and velocity. So these two tools work in tandem to fully describe motion. So let me give you a few examples. These examples are from your textbook. This is example 4.1. Imagine that you have a boat. It's an airboat, so it works by having a fan on the back, and that fan blows air behind it to propel it forward. And this boat has a mass of 350 kilograms, and that fan can provide a force of 770 newtons. Now this is a net force, so I should actually say, I should rewrite this. I should say there's a net force on the boat. Because this net force is the force the fan provides minus whatever resistance force there is from the water. So we'll ask a few questions. What's the boat's acceleration? How long does it take to reach a speed of 12 meters per second? And if the boat stops in 50 meters after reaching that maximum speed, then what is the resistance force on it? we've got 3 questions. First of all, what's the boat's acceleration? Well, let's use our Newton's second law. And for this problem, we're starting out simple. It's 1D. We just have, say, the boat moving forward, and that force so that force is pushing the boat forward. Everything's happening along one line, so we don't need to do 2 or 3 dimensions. So I'll just use an x equation. We can just say AX equals the net force over the boat's mass. That net force was 7.7 times 10 to the 2 newtons, and 3.5 times 10 to the 2 kilograms, which gives you 2.2 meters per second squared for the acceleration. Now part B, how long does it take to reach a final speed of 12 meters per second? This is a kinematics problem now. We've done our Newton's second law portion, we figured out the acceleration, and now we can use kinematics to describe that motion. So remember, our kinematics procedure identified that it's kinematics. I know that it's kinematics because it's now asking to describe quantities like time or position or velocity, which you don't get using Newton's second law. And now we write down our known quantities. We can say V initial is 0. V final is 12 meters per second. We know the acceleration is 2.2 meters per second squared. I kind of dropped this x subscript. It's 1D, it doesn't matter what we label it. And we want to find the time. So we need to pick a good equation to use, and I think the one we want is V final equals V initial plus AT. The initial is 0, and we solve this equation, and we find that the time is V final over A, which is 5.45 seconds. Okay. Now I'm going to erase this stuff to create some room to do part C. Part C is a little more involved. It says the boat stops in 50 meters after reaching 12 meters per second. What is the resistance force? So in this scenario, we're going to need to use both Newton's second law and kinematics. We can use kinematics to figure out the acceleration, and then once we know the acceleration, we can use Newton's second law to figure out the force. I know that because I have prior experience doing problems like this, and if that doesn't seem obvious to you right now, you are gaining experience by seeing examples, and that's how you learn how to do physics. So first I'm going to find A using kinematics. and find F using Newton's second law. Part C is a different scenario than A and B, so the acceleration and force are different than they were in those cases. All right, so let's do the kinematics part to find the acceleration for part C. I just identified I need to use kinematics, so now I'll write down my knowns. V initial is 12 meters per second. We're considering the initial case to be when it's moving at its maximum speed, and we're considering the final case to be when it comes to a stop. We also know that the displacement is 50 meters. And we want to find the acceleration. So we can use, well, which equation looks good? I think this one looks the best. That one's going to do it. And V final is 0, so that term goes away. And we can solve it. A equals negative V initial squared over 2 delta x. Yeah. I didn't bother to calculate this along the way. I had the final answer for the problem though. So we'll just leave it like that. And then the last thing we want to do is figure out what resistance force would be causing this acceleration. And we do that using Newton's second law. We can say A equals F over M. Which implies that this force is going to be M times A. So we just multiply this A by the mass and we get minus 504 newtons. Let me point out something with the signs here. Remember we talked about the signs, the relative signs between velocity and acceleration. When an object is speeding up, velocity and acceleration have the same sign, or they point in the same direction. When an object's slowing down, velocity and acceleration point in opposite directions. Well, if you look at Newton's second law, the net force points in the same direction as acceleration does. So the same directional relationship holds between force and velocity as it does for acceleration and velocity. So this force has a minus sign, meaning it's opposing the boat's velocity. So it's slowing the boat down. That minus sign came from the fact that the acceleration we calculated also has a minus sign. So whenever a force vector points opposite velocity vector, it slows an object down.